Good morning. Anybody have any questions before we get started? No questions. It's all perfectly clear. Okay, so we're starting our journey on dealing with probabilistic descriptions of uncertainty. What we're going to come out with today is a reasonable way of choosing the weight in a weighted least squares problem. So I'm going to try to help you a little bit in the first part of the lecture, get your intuition up. Then we're going to pose a new estimation problem where probability rears its ugly little head and start to work on that. So the two things we need right now is just the mean and the covariance of a random vector. We'll do a more in-depth probability review where we get into conditional probabilities and conditional random vectors before we do the Kalman filter. But for now, all we need is the notion of mean and variance. So if we have a vector, which means each component of the vector is a random variable, we call it a random vector. It has some density that depends upon a number of variables that we're just going to call x1 through little xn. And the mean of the random vector, which we'll often denote by mu, is the expected value of x. And the expected value of anything is you integrate the thing against the density. So it'll put the highest weight on the quantity where there's the most probability of it occurring. So you have a density, okay? So the mean gives you the center value roughly, and the covariance is the spread about the mean. So it is the expected value of x minus its mean, which is an n by 1, times x minus mu transpose, which is a 1 by n, to get us an n by n matrix. It's easy to check that Q is symmetric because it doesn't matter which order that I multiply scalars, okay? So that thing, Qij and Qji are the same. So Q is a symmetric matrix. And you can also check that it's always positive semi-definite. Remember, we said if we had a matrix n times n transpose, it's always positive semi-definite. So that's why that is true. So that's the covariance matrix corresponding to a random vector. It may or may not be invertible. And all the problems we treat, we do the easiest case. Q is actually invertible. Okay, so that means it has no zero eigenvalues. And since the eigenvalues of a symmetric positive semi-definite matrix are non-negative, that means all of the eigenvalues are positive. Okay, so Q is now positive definite. It has an inverse, and that has a name. It's called the information matrix. We see it a lot, but we don't use it explicitly too much in the course, but it's good to know that term, information matrix. So the covariance is an n by n quantity. The variance of the random vector is a scalar. It's a 1 by 1. And so it moves the transpose from the right to the left. So now this is a row vector times a column vector. And it's the expected value of this quantity. Okay, so this, I want you to note that this looks like an inner product. Okay? And so this expectation and the variance, this is really a norm squared. We'll come back to this. We use it a little bit today, but it's really a norm squared of the random vector. So we will eventually set us up, not today, but eventually we will work on an inner product space of random variables, and we'll have a norm that comes from this type of inner product. Now, what is the relationship of the variance to the covariance? As you are studying for your exam, you are reviewing the trace, the thing we introduced in homework 1, or was it homework 2? And we have this little result that you looked up, that if you have matrices that are compatible, no matter which way you multiply them, so this way it's an n by n, and this way it's an m by n, so there, you get square matrices. The trace of a square matrix is the sum of the diagonal quantities, okay? And we have this cute little fact about the trace, that if you flip the order of the matrices, it does not change the sum of the diagonal elements. So that allows us to relate the variance to the covariance, because this quantity is 1 by 1, it's a scalar. So the trace of a scalar is equal to the scalar. And then we can flip the order, and now we have the trace of an n by n matrix. So then if we take expected value here, it's expected value here, it's expected value here, and we see variance equals the trace of the covariance. Okay, so that's the exercise. Variance is the trace of the covariance matrix. And the whole idea is something super deep, okay? A trace is a sum. An expectation is an integral. And we know the integral of a sum is the sum of the integrals. Okay, so that's all it is, okay? There's no mystery here, really. But if you have to write it out, and I didn't do it, so you have to, that's all your exercise is you write out and you realize, yes, the sum of the integrals is the integral of the sum, bingo. The variance of a random vector is the trace of the corresponding covariance matrix. So that's a very useful fact to know. It shows up in lots of different calculations. Okay, I am going to now do a Matlab demonstration. Can you believe it? I've never done one in all the times I've taught this course, but the pitiful looks on your face on Tuesday when I was talking about this motivated me to do this. How do you feel about that? Embarrassed. We're totally embarrassed. No, just kidding. Just kidding. Okay, so I just want to show, what does it look like when the covariance is diagonal, and it's kind of easy to see what's going on, and when the covariance is not diagonal, but yet it's a symmetric positive definite matrix, so we can diagonalize it with an orthogonal transformation. Symmetric matrices are similar to diagonal matrices via an orthogonal matrix. And here's the orthogonal transformation. Okay? So all this stuff will be up there. And so let's go to the Matlab thing, which I want to get out of tablet mode here. Will you let me? Please? Please? Come on. Get out of, oh, you almost let me do it. Tablet mode off. Matlab. Yay! Okay. So here's my little Matlab script. And so I don't expect you to read this. I'll post it. But the first time I have my covariance matrix as a diagonal. The second time it is not a diagonal. And then the third time, I diagonalize it back with my orthogonal transformation. Okay, so let's just see what happens when I run. Okay, everything's really little. Well, that's not nice. Let's look at this one first. So here's a scatter plot of 500 samples. It's a random vector. Okay, the x1 component has variance 10. and the x2 component had variance 1. The mean is 0. Okay, it's a random vector, so all I did was sample the random vector. I just called the Gaussian random variable, I called it 500 times or 300 times, we'll have to look, and I just plotted it. So what do you see? Well, it's a lot more spread out. Remember, I'm sampling something that's 0. Which of these components lands much more often closer to 0 than the other one? The one with the lower variance, okay? That's all I'm trying to show. Question? We got it? Yay! Okay. Now, here's the one where the covariance matrix is not diagonal. What do we see here? It's just a rotated version of what we had before, okay? Along this axis, we have the variance being 10. And along the orthogonal axis to it, the variance is 1. So how do we take something that's rotated like this and rotate it up? An orthogonal transformation, okay? Just a rotation matrix. So that's what it means when we do that. And so instead of rotating it flat, I just rotated it up like this, okay? I could do a different rotation and put it like this. I could rotate it over here instead of over here, okay? They're just rotations. So what I did here was I defined a new random vector, which was an orthogonal matrix times the original random vector, and then sampled that thing, boom, 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 and that's what I get, okay? So does this help to explain what general covariance matrix is versus diagonal covariance matrix versus diagonal covariance matrix? That helps? No? Questions? We're impressed? No, your Matlab plots are kind of ugly, Professor Grizzle, and we would never turn in anything like that. Is that what you're saying? Hey, come on. Does this help, the idea of spread, though? Seriously. Okay, that's all I want to hear. Some confirmation that you got information. Okay. So we can drop, you're comfortable with a covariance matrix. If I write down something has a covariance matrix, you understand it gives you spread in different directions. And if you diagonalize the matrix, then you see the spread in x1, the spread in x2, the spread in x3, and I can't find x4 in the room, okay? But we could do that if we had a 20-dimensional random vector. We'd have a Q matrix that's 20 by 20, and we'd have 20 eigenvectors, 20 eigenvalues, and each eigenvector, because it's symmetric, they're orthogonal, and they give me directions where I can see what's going on. Cool. Okay, so let's go back to this. Okay, because I got lots of funny looks when I took my random vector, which had a non-diagonal thing, and I defined a new random vector by multiplying by an orthogonal matrix that I got by looking at the eigenvectors of my covariance matrix, and then I plot this, and this one, I rotated it more up. Okay, so that's what we've got. So covariance is spread, and when it's not diagonal, we could diagonalize it, but hey, more general case is that. So we're going back to estimation problems, and the ones we've solved so far, there's no notion of randomness. They're just unknowns. So the new one we set up was these underdetermined equations. Y equals Cx, X is in Rn, Y is in Rm, but there's fewer Ys than there are X's. So there's an infinite number of solutions. I'm doing weighted least squares. So I've got my positive definite matrix. I define the norm squared via an inner product. So that these equations are consistent, I have the rows of C now linearly independent. And then I told you the answer was this. If I try to find the x of smallest norm in this weighted norm, subject to x satisfies the equation, then this is the answer. It's a linear function of the measurement. Okay, you calculate a gain times y. Whereas we did the overdetermined before, and first I just gave you the answer, and the only difference is we wrote it as y equals a times x, and so you probably have encoded in your brain that it's a transpose a instead of c transpose c. I know. It's because we like to write down ax equals b for equations, but I'm moving us towards, we have a state variable model, xk plus 1 is axk, et cetera, and these are output measurements. That's where we're moving towards. So I'm slowly moving your comfort zone to writing the y as c times x, because that's the common notation for the output of a linear system, okay? So the overdetermined case, there really wasn't an x to make that an equation. So the only way to really make it an equation is to say that there's something that we don't know that was here, that was on there. And then what we were doing is really finding the x that solves the equation such that I have to cheat by the smallest amount to add something to it to make the equations valid. Okay, so that's another interpretation of what we were doing with the overdetermined. And so once again, S positive definite, we have a norm squared via an inner product. In the overdetermined case, we wanted the columns of A linearly independent, so now the columns of C are linearly independent. And then this is the inverse of the Gram matrix. X is the alpha from the normal equations, and then this is the beta, if you're going back to our normal equations, okay? So x hat was chosen to minimize what we have to add to the equation such that this is actually an equal sign. It's the error in our estimate, and that was the answer there. And then the thing that was driving us crazy, and you guys kept asking me, and just rightfully so, is how do we choose this? Where does it come from? Why do I choose one matrix over another? Initially, when this was just the identity, you're totally happy with that, okay? It just seemed, yeah, sure. Everything is the same. You're the same as me, you're the same as me, you're the same as me, you're the same as me. No, I'm much older, okay? You're happy that you're not the same, okay? A weighting matrix here, okay? So how do you choose it if it's not based upon age? We don't do age discrimination in Rob 501, right? Okay, so that's what we're headed for today. We're going to do the best linear unbiased estimator. Best linear unbiased estimator. Okay, so it goes by blue. And when we come out of this, we're going to go back to the overdetermined case, and then you will understand, yes, that's my choice of the weight matrix. So that's our goal. Okay, so our goal find out how to choose the weight matrix. choose the weight matrix in an overdetermined problem. So that's our secret goal. But first, let's just understand what does the word linear mean, what does the word unbiased mean, what does the word best mean, and then we'll have a best linear unbiased estimator. So here's the problem setting. Y equals Cx, and I'm going to call this epsilon. Y is our measurement. It has m components. X is our unknown state. It has n components. And epsilon, hey, they look a little bit different. It's the same size as y. Now this is going to be an overdetermined problem once again. So I am going to eventually assume columns of C are linearly independent. What's going to be different here is I'm now going to give you a model. We're going to assume a model for epsilon, which is the noise. Okay, so noise model. We will assume its mean value is 0. Later in homework, you can rederive this when epsilon is not equal to 0. Okay. And the covariance of epsilon is Q, and that's positive definite. So what is different now is we have a model for the perturbations that are showing up on what we think is our deterministic sensor model. Now what is X? Whoops, on a different color here. Come on. X is an unknown constant. But unfortunately, in this problem, we have no side information about X. We have no idea what its mean is, and we have no idea what its covariance is. I have no information on X, only on the noise perturbation. That's this problem formulation. Okay? A little bit farther down the road, we will do another version of this problem where we have a noise model and a stochastic model for X as well. So we're just taking little steps before we get there, okay? So X is just an unknown constant. Please, yes?
The noise model related to the sensor noise?
Yep, it's, I'm measuring the value of my angle via an encoder, but I have no idea what vibration have caused the thing to be in between the quantization of my encoder, etc. Okay, so it's that. Okay, so no noise model for X. Now, just vocabulary. One says X is deterministic while this epsilon thing is stochastic. Okay, so it's just vocabulary. But if you hear it, it's good to know it. Okay, so X is unknown. We want to find X based upon Y. What's the best value for X? So this is just the problem. So let me define the terms in linear, unbiased, and best. Okay? Well, linear, I bet you're going to be super surprised. We seek x hat is k times y. A linear estimator. Okay. I mentioned this, but I forgot it. I wish I had done it first. We're going to assume the columns of C are linearly independent. Okay, so I really would have liked to have had this as still part of the problem formulation, but that's life. Life is hard. My brain is not deterministic, okay? It is stochastic. So this is the linear part. Linear estimator, I recover x, that's my estimate of it, from y with a linear operation, just a gain. Okay, now, what's the unbiased part? So, definition, x hat is an unbiased estimate, not of, if you take the expected value of x, what do you think you would like to get? What are we trying to estimate? We're trying to estimate x. You'd like the average value. So, let's be clear in this problem statement. This is noise. So even if this is a constant, this is now a random vector. All I've done is bias this random vector by this thing. So this is random. X hat is k times something random. X hat is random. What do you think I want its mean value to be? X itself, right? It's got to be x. Okay? That means it's unbiased. Okay? It's the value of the unknown constant. Okay? Turns out that's a pretty wicked constraint. Okay, so let's figure out what that means, okay? So if we have x is equal to the expected value of this estimate, and this expected value is k times y, and so that's k times, and y was cx plus the noise that's perturbing our measurement, cx. So that's the expected value of kc times x plus k times the noise. We're good with this so far? Just plugging in x hat is k times y and multiplying it through. Now an expectation is a sum. So the expectation is an integral. This is an integral. So the integral of a sum is the sum of the integrals, right? So we just go one more step. That's easy. Okay. This next part is either obvious to you or it's not. It depends on your familiarity with playing with random variables and stuff. So this is just a constant matrix. So we can take the constant outside of an integral. And the expected value of epsilon is 0. So this is 0. We're good with that. I think that part works. Okay, now, here's the thing. X is an unknown constant. So is C. C is a constant and K is a constant. So we can take all of this outside. Okay. So this part is KCX plus 0. Okay. So this is the part that you may want to come by office hours and we play with this a little bit. But let's take it like this. Okay. So X is unbiased if its expected value, X hat is unbiased if its expected value is equal to the unknown constant. And so we have the equation X equals KC times X. So what do we need this to be? Yeah, it's got to be the identity, okay? So we have this, unbiased, if and only if X equals KC times X. So that's a constraint when we choose this gain, and that's not an X dot, okay? And then it's an easy fact or an exercise for you that X equals K times CX for every X in Rn if and only if K times C is equal to the identity. And just to be clear, that's an n by n identity. It's going to be very useful for me to keep this notation. Okay, so it's clearly a sufficient condition. If K times C is the identity, then X equals X, okay? But if this only had to hold for one particular X, you could find lots of matrix combinations that give you that one X back. But if you want it to work for all X's, it's a very strong restriction, okay? So that has to be a constraint. Okay, let me go back and we'll keep building it up. Blue, best linear unbiased estimator. So linear, that's X hat equals KY. Unbiased, that's KC equals identity. So what is best now? That's what we're heading towards. So now we're going to do best. Whoops. Okay, so X hat is a random vector. We're going to use best as terms of we're going to choose the gains to minimize the variance of X hat. That's going to minimize the spread about its mean. That makes sense? That's a really good term. So that's what we're going to do. Best is minimize the variance of X hat. Okay? So that means we need to do this. Choose our gain in our estimator such that we minimize, not mimic, the variance of x hat while constraining k to give us an unbiased estimator. Okay, so that's going to be our problem. So let's figure out a formula for what the variance of x hat looks like, and then we can minimize that. That's what we're going to do. The logic of this is coming through, I hope. Okay, so let's find the variance of x hat. Let's try to get blue. One more time. There we go. Variance of x hat equals expected value x hat minus its mean, okay, it's unbiased, times x hat minus its mean transpose. Okay, so I'm going to now rewrite this in terms of a trace of a covariance matrix. Okay, so I'm going to use those tricks, and the reason we're going to do that is because that's the information we have in our model. In the end, we know our model gives us the covariance of the noise. So I'm going to rewrite the variance in terms of trace of covariance to make this matrix show up. That's all I'm doing. Okay, so I'm just going to, we've got this variance. So let's just look at these terms. X hat minus x. X hat is k times y minus x. Y is Cx plus the noise term minus x Yep, hold it together, I won't look. Kc multiply through times x minus the x over here plus k times our noise term on the measurement. Because k is restrained to be unbiased, this adds up to 0. So this is just k times epsilon.
Rewrite the variance, because earlier we wrote it as x minus x transpose times that, and so this would be the code.
This is the covariance. Thank you. Yep. I wish I could claim that that was just a test to see if anybody was paying attention, but it wasn't. Just a blooper. It's a blooper by the professor. Okay, the variance should be a scalar, row vector times column vector. Yay, it's 1 by 1. Thank you. And now we look at what does these terms look like, and it's just the unknown gain that we're trying to choose to minimize this variance times the noise. Okay, so then, let me change color again, just because I like to, even though my pad is not liking me to do it. So, the variance of x hat is now equal to the variance of the random vector k times epsilon. And that's expected value. And thank you for getting my transpose in the right place. Very important. So this is a scalar, so I can slip in a trace right here and not change anything. So this is that trick we looked at earlier. So it's trace, K epsilon transpose K epsilon. And the cute thing about the trace is I can change the order now, K epsilon, and move my transpose of some very ugly quantity the way I had written it, and there's no bar there. Okay, so trace of a scalar is the scalar, and trace is indifferent to which way I write these as long as it's still compatible. And so I keep going relentlessly with this, and I get K epsilon, epsilon transpose, K transpose. And then the final coup de grace. Expectation is an integral, a trace is a sum, so I can move the trace outside because integral of a sum is the sum of the integrals. K is a constant, I can take it outside the integral. K transpose, I take it outside the integral, and I'm left with expected value of epsilon, epsilon transpose, which is the covariance of my noise, okay? I just told you, we had to go through the mental gymnastics so that we could, so it's trace, K, expected value, epsilon, epsilon transpose, K transpose, and so it's the trace, K, Q, K transpose, okay? So that's a big formula. Okay, so this problem is forcing us to sort of rub our bellies and pat ourselves on the head. Let you get this written down. Let's make sure the logic is flowing, and then we're just going to write down what the problem is. I'll then give you the answer to it, and then we'll do the derivation, and you'll pay attention to that as much as you want to. Okay? Okay, so we're trying to choose the gain of our estimator. It's linear. X hat is K times Y. We're trying to choose that gain to minimize the variance of X. So we need to minimize this quantity, and it needs to be unbiased. So we have a constraint, K times C equals I. So here's our new problem. X hat equals K times Y, and we seek K satisfying okay, so I'm going to call this K hat. K hat. K hat equals arg min of trace of K Q K transpose, subject to it being unbiased. Okay, so that's our estimator now. It's linear. We choose the gain to minimize this quantity. It minimizes the variance of our estimator, and this constraint makes it unbiased. So that's our problem. So what does that look like? Does it look like anything? Well, it looks like better than average handwriting, okay, but that's not really what we're after. Let's go back up here. It looks like this, which is the variables are totally different names, okay? It's minimizing the norm of a quantity subject to a linear constraint. Huh. Okay. This is really an underdetermined problem. This is a weighted norm on the set of matrices, okay, with a linear constraint. So this is the problem. I'm going to give you the answer, then we're going to take this problem all apart and show you how to solve it. But okay, save that so I don't screw anything up. Please open it up. Oh, recorded lectures, images, today, bingo. Okay, so you can ignore this very top part. So if you go back and look at the x hat, it looks exactly like this. Okay, so we will get it from the underdetermined equations. Okay, but what I want to really point out is when we solved the overdetermined problem, and the answer was, we had AX equals B. If this is the identity matrix, then the answer is X hat is K times X, right? And this is the A transpose C inverse, and then A transpose times the B, okay? So this is the weighted least squares solution when you choose the weighting term to be the information matrix, okay? So remember, the information matrix is big where the covariance matrix is little. Little means not much spread. We have lots of confidence in that component of the measurement, okay? And so it's giving big weight to the components of the measurements we trust and much smaller weights to the components of the measurements we don't trust. Okay, so we're going to go through the derivation, but the thing you really want to get out is summarized here. So the derivation you will not be responsible for, but oh, don't do that. Cancel. Cancel. So you need to know this, this, and also derive the variance. Okay? No big deal. Take the trace of this, okay? That's the variance. So the key point, blue equals weighted least squares with weight matrix equals the information matrix. And that's the inverse of the covariance of the noise. Okay, so you guys aren't looking at the final exams, but there's free points lying all over final exams when I ask you questions on how is least squares related to weighted least squares is related to blue, and then we'll do the minimum variance estimator, and they're all tied together by little facts like this. So you can do weighted least squares, you can do unweighted least squares. Unweighted least squares just means the covariance of the noise is the identity, okay? That means you don't really know anything. They're all the same, okay? So when you're doing unweighted least squares, you are choosing the covariance of the noise to be the identity. Well, why not, okay? Why not? But if you have more information than that, then you can use it and you choose the weight to actually be the inverse of the covariance matrix, which is the information matrix. So, bingo. So there's the solution, and then the weighted least squares overdetermined. You plug in S equals Q inverse, and you now have the weighted least squares. Okay? What do you think? You want to see why that's true, or is it just enough to know that it's true? About half of us kind of think we might be asked about that on a qualifying exam or something, and the other half go, I don't think my boss will ever ask me to derive it for him, okay? And when I'm racking up the big paychecks, it'll still all be good. No, I'm with you on that, okay? Okay, so best linear unbiased, linear, x hat is k times y, unbiased, kc equals identity, best, minimum variance, okay? And our problem is, this is the variance of x of our estimate, minimize that subject to this. So let's see why that turns out to be an underdetermined estimation problem. Okay? Questions before we start on that little adventure? Works? Okay. Okay, so let's go back to, okay, deriving answer and relating it to underdetermined equations. Okay, so here's step one. We're going to take K, and instead of breaking it up into its columns, we're going to break it up into its rows. Whoops, K, X equals K times Y, and X is in Rn. So K has N rows. So that's what K looks like. Okay. So then what does K transpose look like? Well, it's the first row transposed, second row transposed, nth row transposed. What is the trace of K, Q, K transpose look like? So this is another reason why we care about partitioned matrices. And surprise, surprise, you have partitioned matrices on your midterm, okay? So good time. This is just review. But this is one of the big reasons we care about partitioned matrices. Okay, let me do one more step. K1, K2, dot, 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 Kn. Now what do I get when I multiply Q times a matrix dividing up into its columns? It's just Q times the first column, Q times the second column, okay? It's not that it's hard, but you guys didn't know that stuff very well when you came in here, but now it's like second nature, which is cool. Q times Q1 transpose, Q times Q2 transpose, Q times Qn transpose, okay? Okay, I'm going to surprise you by how easy and cute this formula looks like for K times Q times K transpose. Okay? It looks completely terrifying. Now, when we do the trace, which elements are we adding up? The diagonal. Okay, so if I take a matrix and multiply it times, if I take rows and I multiply them times columns, how do I get the diagonal terms in that matrix? Well, what's the 1, 1 term? First row times the first column. What's the 2, 2 term? Second row times the second column. What's the n term? Nth row times the nth column, okay? So this is just equal to the sum, I equals 1 to n, of Ki, Q, Ki transpose. Isn't that amazing? Okay, so what is that equal to? Well, that's the norm of the ith row squared when my weight matrix is Q. Okay, so it's just a sum of a whole bunch of terms. Questions on that? It works? You can do your partition matrices on the exam and you're very confident of getting them all right, correct? We're going to try. Okay, so just remember, trace is rows, columns, and you only care about the things on the diagonal. So you don't have to take the first column times the first row times the second column. You do to form the matrix, the ij element is Ki and then Q times Kj transpose, but we only care about the diagonal. So that's the trace. It just pulls out the diagonal. Okay, so that's what this norm looks like we're trying to minimize. It's just a sum of a bunch of individual problems. Whoops, I forgot my sum sign here. You guys were being polite and seeing if I would even notice. Okay, I did. Good. Okay, what about this Kc equals the identity? N by n. Well, this part is kind of a trick. You have to know the answer, but if I transpose it, I still get the identity, okay? I haven't changed anything. So that's if and only if I have C transpose, and then K transpose, we've done this. It's little k1 transpose, the second row transposed into the column, kn transposed, okay? Equals, okay. And I'm going to now write the identity as the first unit vector, the second unit vector, and the nth unit vector, okay? EI is 0, 0, 1, 0, 0, ith row. Okay, so I'm trying to break this KC thing down into something that I can work with vectors instead of matrices. And so I get Kc equals In by n if and only if C transpose Ki transpose equals Ei. Okay, so that's the unbiased condition. This should hold true for 1 less than I less than n. Okay, so in terms of meeting this unbiased condition, how is the first row of K related to the second row of K related to the third row of K? The answer is they're completely decoupled, okay? They don't depend on each other. Okay, there's not a K1 plus a K2 plus something equals, which would make it all tangled up, okay? So this constraint is independent and independent constraints in that matrix equation. Okay? And the thing we're trying to minimize is a sum of individual terms. So minimizing that sum is the same thing as minimizing each of the individual terms subject to its individual constraint. Okay, so it decomposes into n independent problems. That's a good trick to know about. Not necessarily for your exam, but for your work and stuff. The problem decomposes into n separate optimization problems. K hat I transpose equals arg min the Q norm squared of K sub I subject to C transpose Ki transpose is the ith unit vector. So now we see the underdetermined least squares problem. Just pops out from the sum. Okay, you get that written down. We'll go back, do it. Then we'll just plug into the least squares formula because you haven't had a chance to derive it yet, but you will do that after the exam. Okay? So the thing we're trying to minimize is the variance of x hat, and that's the trace of K, Q, K transpose, and that's the sum of Ki squareds. The unbiased Kc equals identity is the same thing as C transpose Ki transpose equals Ei. So we're going to individually minimize each of the rows of our gain matrix subject to this linear constraint. And so this is an underdetermined least squares problem. And then, so we go back to the formulas, which we do that with S equals Q inverse, and we get this. And I don't have it memorized, so I'm going to write it down here carefully, times EI. Yeah. And so k hat, that's k hat transpose 1 dot 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 k hat transpose n. So this is the ith column of it. It's, when you do it, you get Q inverse C, C transpose, Q inverse, C inverse. Whoops, transpose. Okay, this is also reviewing for the exam. Tell me how, a short way to write down that this is correct, okay? If I multiply this by the identity, what do I get? I think, okay? Now, if I take this matrix and I multiply it by the ith column of the identity, what do I get? Okay? This matrix times the ith column is this. Okay? Everybody agree now that that's k hat transpose? It's just partition matrices, okay? So if this stuff is not working for you, you got to practice more for the exam, okay? It's just, okay? Just partition matrices, okay? So those will be assumed that this would be a simple partition matrix problem. Okay, so that's it. So there's our formula. Okay, that's where it came from, and then we go back to the theorem. This is what you guys will want to know for the final exam. Best linear unbiased estimator is a linear estimator where the optimal gain satisfies this quantity. This is the covariance of the estimator. And if you derive the variance of that, it's just a trace of this quantity. So we've minimized the variance of our estimate, best linear unbiased estimator. Bingo. That's it. So if you're happy, I'm happy, and we're done for today. You want to do more? No? I know Nils let you out early. Well, I was gone, okay. So I fired him. No. So I figured if he can let you out early, I can too. So we're going to stop today. Tuesday, we have the exam. So there's review sessions on Sunday night. It's posted by me. Monday evening by Nils. So you get to talk to each of us. Tuesday in lecture, we'll do half a lecture on something, the QR factorization. The nice thing about that is it uses Gram-Schmidt, which is on your exam, so it's good review, okay? This stuff is good review. It's all partitioned matrices, traces, stuff like that. Today was good review, preparing for the exam. This material's not on it, but partition matrices, traces, that's on the exam. We'll do half a lecture on the QR factorization, and then we'll do other half additional Q&A. And then you'll have office hours after that with me. And then you should be super ready for the exam, okay? That's the idea. Now, I missed office hours on Tuesday, because half of them, so I'm happy to go up to my office between now and 12:30 if you guys want to come by and ask questions now to make on homework or lecture or anything. Thank you for your attention and participation. And the less quizzical looks today and the more nodding like you pretended you understood. So thank you.